Hello everyone. So far we have seen the vanilla SGD. In this video we will see the momentum version of non-convex case. Let us first consider the context. We have already seen that using a momentum term we were able to accelerate the vanilla gradient descent, and that led to us being able to accelerate the entire class of deterministic algorithms like proximal and so on. The momentum idea is, however, not directly applicable to stochastic gradient descent, and it has been seen that the stochastic version of Nesterov's accelerated gradient descent is not better than SGD in practice. In fact, the presence of noise nullifies the effect of the momentum term as used in the Nesterov's accelerated gradient descent. Over the years, people have proposed heuristic versions of momentum SGD, and they have been widely used. These include algorithms like RMS prop, Adam, Adagrad, and so on. There is a huge list of these algorithms and they have been widely explored. For instance, the paper where Adam was proposed has thousands of citations and it is widely used, although its theory is not entirely correct. And empirically, people have shown that it does not always outperform vanilla SGD. Indeed, none of these algorithms outperform SGD in terms of IFO complexity for general non-convex settings. Hence, theoretically, the role that momentum could play in improving the performance still remains unclear. This is perhaps very surprising because both SGD and AGD are decades old and people have been studying them extensively. A novel recursive momentum idea has been recently proposed in this reference, where the authors call the algorithm STORM, that was able to improve the IFO complexity from 1 by epsilon raised to the power 4 to 1 by epsilon raised to the power 3. This result is remarkable because it is one of the few that shows theoretical improvement for non-convex problems. So let us look at the assumptions. In this case, we need stronger smoothness assumption. Specifically, instead of requiring capital F to be smooth, we now require that f of x comma xi is L smooth with respect to x. This assumption obviously implies that capital F is also L smooth, but is stronger. So converse is not necessarily true if we allow n tending to infinity. Secondly, we assume a simplified version of the bounded moment condition. That is, we assume that expected value of norm square of gradient f of x comma xi t minus gradient f of x is less than equal to sigma square. Recall that earlier we had the additional term depending on the norm square of the gradient of capital F of x. Here we have dropped that term, or you could say that we have assumed that c equal to 1 in that assumption. We have made this assumption just for the sake of brevity. However, the assumption for most general case of this is almost similar with a few additional steps and will give the same rate. Henceforth, we will use the notation that capital delta of t is equal to expected value of norm square of gradient f of xt. Let us then come to the STORM algorithm. Let us first write it down. So we initialize x1 arbitrarily and then set d1 is equal to gradient of f x1 comma xi1, where xi1 as usual is the randomly selected data point. Then at iteration t, we update xt plus 1 equal to xt minus eta t dt and dt plus 1 equal to gradient f of xt plus 1 comma xi t plus 1 plus 1 minus alpha t plus 1 times dt minus gradient f of xt comma xi t plus 1. So observe here that STORM requires two IFO calls per iteration, actually two evaluations of gradient f of dot comma xi t plus 1. The direction in which the updates move is given by dt and is calculated by using an additional term added to the current stochastic gradient. So obviously if alpha was equal to 1, then this would become the vanilla SGD. However, when alpha is not equal to 1, and in fact we will choose alpha carefully to get the required rate. We will consider the following choice, which is that eta t equal to 1 over 4L cube root of 7 by t plus 7 and alpha t plus 1 equal to 16 eta t square L square equal to 7 by t plus 7 raised to the power 2 by 3. And for this choice, the result is that the oracle complexity is given by order of LBF raised to the power 3 by 2 plus sigma cube log of 1 over epsilon divided by epsilon cube. A slightly better oracle complexity is obtained when using adaptive step sizes, and that is described in the Storm paper, and you can look at it there. In this video, we will only consider the simpler version. Note that the updates can also be written equivalently as dt equal to 1 minus alpha t into dt minus 1 plus alpha t into gradient f of xt comma xi t plus 1 minus alpha t into gradient f of xt comma xi t minus gradient f of xt minus 1 comma xi t. Xt plus 1 equal to xt minus eta t into dt. The way in which dt is tracked is referred to by the authors of the Storm paper as recursive momentum. From the update of dt, we can guess that the purpose of this update is to ensure that dt is approximately gradient f of xt. A major part of the proof will in fact be devoting to characterizing how well dt is able to track the gradient of the objective. We will denote et equal to expected value of norm square of dt minus gradient of capital F of xt. And we will essentially show that et decreases at a certain rate with t, which will then allow us to show the rate at which delta t diminishes. So that is all for this video. We will look at the detailed proof in the next video. So basically there are 3 key steps to the proof: deriving a recursion on et, deriving a bound on delta t, and finally combining the 2 bounds so as to ensure that the telescopic sum is achieved. While the derivations are slightly longer, the overall proof outline is somewhat similar to accelerated gradient descent. So we'll continue in the next video with the full detailed proof.